Should be recording. All right, cool. It's recording. All right. And then tomorrow we are going over integration by parts and integration using partial fractions. There's 2 examples on the practice final as well to go over that. The practice final that was emailed to you, it's basically what your final is going to look like, and we're going to be visiting that every single time. So basically we're going to be chopping down that practice final until we get done with all the content. That way you kind of know what the final is going to look like and what the quizzes are going to look like. All right, so Thursday, hopefully you can see this. Let's blow this up. Nope, that doesn't help. All right, Thursday, the quiz is canceled because you literally only had 1 day. Just if we had today's lesson and then tomorrow's lessons, you have 1 day before the quiz, which is kind of stupid. So what I'm going to do is reschedule it for next Monday. Every Monday is now going to be a quiz day. We'll go over that in a little bit. The quiz is going to be on everything we're going over this week. Okay, that's how all the quizzes are going to be. It's all going to be based on the stuff that we went over the week before. So the new schedule is going to be, instead of those Thursday quizzes, it's quizzes on Monday. So this it says right, allows more days to grasp the material after it is first introduced. So we're going to have a lesson on after this week. We're going to have a lesson on Tuesdays and Wednesdays, and then you have the entire, basically a week to assess on that, which is on that Monday. It just doesn't work for this week because our first day is on a Monday and we can't quiz on the first day. I'll show you a calendar later so this makes more sense. Live lessons are going to be Tuesdays and Wednesdays after this week. I did update the lesson times spreadsheet here. This loads. So it says like Monday quiz day, so you can sign up for Mondays, Tuesdays, and Wednesdays. It's just this week's a little bit messed up. So this day right here, this Thursday assessment's not going to happen. So you don't need to worry about a quiz this week. There will not be one. And this is to your benefit. So let's see here. Next, I wanted to go over the questions that people ask. You probably can't read that because I can't zoom in any further. But actually, I should be able to. Can you see that now? Anybody just chime in?
Yep.
All right, cool. So you did that student information form, and then one of the questions was, what do you want to know about me? So I kind of broke down all the questions into like categories of what you want to know about me. This first one, it says like, didn't read the question on the form. So the question says, what do you want to know about me? And people wrote, I'm from Nebraska. I'm not good at doing online classes. I am someone that continues to work, blah, blah, blah. The question was, what do you want to know about me? So, but that happens every year. I should rewrite the question or something. But for the teaching questions, it says, where have you taught? I am currently, I'm a high school teacher at Batavia High School. I teach AP Computer Science, AP Calculus there. And I've been there for 6 years. Actually, I think that's one of the other questions. I've been there for 6 years. I've been teaching for 16 years though. And then I've been at this community college for 6 years. It says, how hands-on are you going to be as a professor? I mean, it's online, so I don't know how hands-on I can be, but I like one-on-one meetings with students or small groups. That's why there's only 12 people that were invited to this today, just so people can ask questions and interact more rather than having 36 people all at once. I do tend to get into the trenches with students, like when I taught or when I was in the high school. I'd like to sit next to them, not just be at the board the whole time and just having conversations. So I guess that's more hands-on. I don't know. I don't understand that question, I guess. On a scale of 1 to 10, how hard do you grade exams? This is so the scale is a little bit screwy with this because it's like, how hard do you grade exams? I feel like people think a 10 is unfairly grading. Like there's some professors that, you lose 50% of the points because you messed up the units or something like that. So how hard I guess the scale is on 1 to 10. How fair do I grade? I tend to grade pretty fairly. I do offer remediation or like reassessment. So if you do really bad on a quiz, you could fix that grade. So I feel like that's pretty fair. We're going to go over how I grade in more detail later on after we take a quiz or a test, just so you can kind of see what my grading looks like. We might touch upon it today a little bit too if there's time. But again, I'm trying to keep this under 2 hours. The next one says, are you going to teach Calc 3 for the fall? Not that I know of. They didn't ask me to do that. That they might. I don't know. I've taught Math 107, which is stats. I've taught Calc 1 at the community college. I've taught Business Calc at the community college, and now I'm teaching Calc 2. So I haven't taught Calc 3 yet, though, but I totally would. Why did you decide to become a math professor? I taught dual credit at Batavia, and they basically asked me if I would be willing to be an adjunct professor. just to help out, fill in for the summer, and then sometimes in the spring. And I just think it's fun. I mean, you get a little bit of extra pay, but it's not really that much, but it's just fun. It's a job that you can walk away from. Any job you can walk away from, I tend to love, because I still have my other main job. So it's just nice. It's a lot easier than high school because you don't have to worry about parents and administrators as much, because you're kind of on your own. So I don't know. They offered me it. I tried it out. I ended up liking it. So stuck with it. How long have you been teaching for? Okay, I kind of talked about this before. I've been teaching for 16 years, or I've been in education 16 years. I used to be a department chair too, so I wasn't always teaching. I was an administrator for a little bit. What inspired you to become a math teacher? Growing up, I always, my family always said, you're either going to be an engineer or a doctor. Even though I didn't like designing things, which engineers design things. I don't like designing things. I've never, I was like, oh, I can't wait to design things. Doctors, a lot of people try to become doctors more because of the money, I feel like, rather than actually taking care of people. Sometimes their motivation's a little bit askew. So I didn't want to be an engineer or a doctor. And I always just kind of looked up to math teachers. I always thought they were like my heroes. They got me to think, and I just always am interested in that kind of thing. So that's kind of why I became a math teacher. I used to be a musician, and I needed summers off too for going on tour and stuff like that. So teaching kind of just resonated with me just as a person. I mean, I don't do any of that stuff now, but I don't know. How long have you been teaching calculus for? This is my 7th year teaching calc. Or actually, no, I taught it at other schools too. I don't know. It's been almost a decade of teaching calc. It's been a while for that. What inspired you to go into teaching, and more specifically calculus? I was always just good at math. I couldn't really make a living off of anything else. So good at math and stuff with computers. And I used to teach chemistry as well. So I was just good at, this is so boring. Why for teaching math? Why did you start teaching? Kind of already talked about that. What is your mathematics history as far as a career? Okay, so my first major was computer engineering. And then I realized I didn't want to be an engineer. So I switched to chemical engineering, thinking it was more chemistry related. Because I liked chemistry, and it wasn't. So I just got a degree in chemistry, and then I worked as a chemist for 2 years. Then I went back to school because I was still doing music at the time, and I was like, oh, I'll just go into teaching. While I was doing that, I started working at Fermilab, actually in Batavia, coding, just doing some programming stuff with computer science. Got my teaching degree, started teaching in Aurora. Then I went to, well, do you want me to go over that? But I've been at 4 different schools. So that's so I have actually used math in the real world, just being a chemist and doing stuff with computer science as well before I taught. Have you taught an online class before? Yes, but it was mostly because we were forced to, because the school ended early or whatever. But I'm kind of learning as I go here. I'm going to try to make it where it's more personable as possible too, but I'll take any suggestions, anything to make this class better. Just let me know. All right, animals. They always get questions on what's your favorite animal. I love otters for whatever reason. I think just because they're cute and they slide on their belly. I don't know. I'm weird about that. Do you have any pets? No, but I'm going to be getting a dog soon because I'm moving actually in a month, so I'll be in a bigger place. So I'm going to get a dog. Math. What made you interested in math? I was always just good at it. People tend to gravitate toward what they're good at. Music didn't work out, so math was a fallback. What is your math calculus history? I kind of talked about that. Blah. Some people don't write anything. Former student. I had a former student that just said, I already know a lot about you. Blah, blah, blah. Are they in this? I don't think they're here. No, they're not. Oh, yeah. My mic is bugged at the moment. Oh, yeah. What's up, Steven? Yes. A couple of students are actually that I've had in the high school are here right now. Lath is one of them. And then Steven's the other one. Yes. Okay, cool. It's really weird when you get a parent of a kid that you had in the high school, because I had a parent one time of a student that I used to teach at the high school. Okay, let's see here. Where am I at? Former student. What school did you attend for undergrad? So I went to Purdue for my undergrad for both of my bachelor's degrees. Then I went to Concordia University in Chicago for my first master's, which is in like educational leadership, to be like a principal, which I never would want to be a principal. And then my second master's was in math at Aurora University. What do you do besides teaching? I play a bunch of instruments. I have a newborn son, and then my other sons, I have 2 sons, and The other one's 3. So they take up a lot of my time. And your favorite movie my favorite movie is Forrest Gump. Do I like Star Wars? I do, but like the original trilogy, the newer trilogy is pretty bad in my opinion, but no, I'm going to get somebody mad, I'm sure. And then comics. Do you like comic books? And if so, which side are you on, DC or Marvel? I do like comic books. I tend to like Batman comics, but the movies, I would say I'm more Marvel just because the MCU is better put together, I'd say. We could talk about that another time. All right, next thing here. Okay, majors. If you want to know anything more about me, just ask. I'm pretty boring. All right, next thing, student majors. You all wrote your majors in, what you're planning on majoring in or might major in. And you can see most of it is engineering. A lot of people wrote engineering. And you do have to take 4 years of calc, generally speaking, for your engineering degree. So that being said, I expect a lot of people not to be complaining about the hard work that is required in this, because Calc 2 is, no offense, it's just nothing compared to Calc 4. I had to take Calc 4 for my chemistry degree. And I could say that it's way more difficult than this class. So if you're complaining already about the difficulty of this class, just know that it gets a lot worse. Not worse, but just more challenging. So undecided, but mostly people here are all STEM related fields: science, technology, engineering, math, econ. You'll definitely need Calc 1. Political science, I'm not sure you actually need to take this class. You're probably better off taking an easier math class, but for everyone else, it's basically a huge weed out class with the calculus. You don't really necessarily need all of the, the stuff that we're learning about, but the skills that you're going to be learning about, you're going to need. Some teachers. Okay, so there's 2 people that are teachers. Minor in computer science. That's very, very wise because it's easier to get jobs that way when you can teach computer science. Planning and architecture. I don't know. Either way, it looks like there's a lot of pretty rigorous majors here, so should be hopefully a good challenge for you with this class. All right, email. Check your email often. I mean, it's an online class. Just try to do it as much as you can. I'm not saying be glued to your email, but it helps. Practice final exam. Okay, this was linked on the website. I'm going to show you where on the website. I also emailed this to you, but it's basically so you understand exactly what's expected of you. Because there's so many, the SAT, you know exactly what's going to be on it. The ACT, you know what's going to be on it. The MCATs, all those exams that you have to take in your life, the driving exam, you know what's on it. So I want you to be able to understand what's going to be on the final exam, just because you should know what's on it. I mean, it's only fair. The final exam problems are also going to be the quiz problems are going to be based off these problems as well. There's only 16 of them on here. So it's a very, very light practice final. Just the important things. And I'll show you where it's linked on the website. I think that's on the next slide. Note, I add problems to this document that I think would help. So every now and then I will add problems to it, but I'll notify you when I do that. And then it says you should be able to complete this fake exam before the end of the course. It's not graded or anything like that, but just so you know what's expected of you. Okay, the website. I would follow along at home on this. It's just mrozarka.com. I guess I can show it here. mrozarka.com. And it brings you to this page. I emailed you about this, so hopefully you actually read the email and did what you were supposed to do. I just wanted you to kind of tour this thing. The main thing that you need is, actually, I made a one-stop shop for everything Math 132 related. So if you go to Calculus up here, the drop-down menu, it just says Math 132. Everything here is what we're going to cover, as well as there's a calendar on the bottom that we're going to go over as well. And then you can see right here, this is actually a link to the live lesson. I shouldn't have done this because now I'm going to hear myself, but it's actually like the lesson that we went over. It's a video. It's just like what we're doing right now. It's just a screen grab of the problems we're going over. So if you ever do miss a lecture, it's just, I'm going to put them up online anyway. So you can see it that way. They'll all be linked here. The practice finals right here where it says practice final exam. You click that. It's all loaded right here. We're going to go over this again toward the end today. Syllabus is linked here. I have to go over that. Online text and the solution guide. The online text is right here. The solution guide, if you've ever seen Slater, it's an awesome website. Users basically go in and put their answer keys in there. I started doing it. It's pretty fun. It just helps people out, and they comment, "Oh, thanks for the help." And I'm like, yeah, no problem. I had to make an answer key for my class anyway. Might as well just upload it. If you haven't seen this website before, it's awesome. You could look up pretty much any book, and even if the answers are just the odd ones in the back, people just again, user generated answer keys for everything. And it's solutions too. They show the steps. Not every problem they do. So I'm trying to like fill in the ones that they don't do. Like they usually skip, a lot of people skip the easier or the harder problems for the, but it's either way, it's a good website, and you can throw in like any text you want, like any textbook, they usually show up there. I'm sure you've heard of it. Practice final. I had to link this resource guide for COVID-19 from the school. All right, I have to go over the syllabus. It's the most boring thing. I'm going to go really fast, though. I'm sorry. I have to go over this. Again, this is just because that's what the syllabus they sent me said. Here's all the stuff that we're covering. If you did take Calc 1 at a different school, just know that some of this will be a review because Wabanzi does Calc 2 a little bit differently than other colleges do. Okay. I am used to teaching. I've taught AP Calc 1, and a lot of this stuff is covered in AP Calc 1, and then some of it's AP Calc 2. You'll be able to see the difference between that, but some of this, again, might be a review. A lot of it won't be. Most of it won't be, but some of it will be. You probably don't recognize some of these words yet, so I'm just going to skip it for now. This is stuff they make us put in the syllabus, so if you want to read through that, you can. Okay, the grading. Okay, so this is kind of going to answer that question of whether I grade fairly or not. So it says the exam is 50% of the grade, midterms 25%. What ideally I want to do, I have to get this approved because I don't know the rules they have. Sometimes some professors are more lenient than others, and others get mad because, you know, we're supposed to all have the same kind of difficulty level. But what I want to do is make it where your quizzes are your grade, just your quizzes, and then the midterm weeks. So you have this midterm exam, this final exam. Whenever, again, I have to get this approved, so I'm sure it will be though. But the quiz grades basically are your grade, and then if you do poorly, like say you do poorly on quiz 1, you can make it up this week. So this week that there's nothing going on besides reviewing, instead of taking a midterm exam, you can just fix that stuff in quiz 1. Or you can fix the stuff in quiz 2. If you want to fix all 3 of them, then might as well just take the midterm exam. Okay, this also helps with, like, say you just can't make it on a Monday to take a quiz. Well, then you have to make it up this week. Okay, and then these 3 quizzes you can make up this week. Now, it doesn't say that in the syllabus, again, because I just kind of made this up, and I don't know if I'm allowed to do this, but that's what I'm thinking. Everything's quiz-based. I emailed someone, and they said it was a good idea. I forgot. It's one of those students. So, I don't know. It's to your benefit. If you want to take the midterm, absolutely, then take it. I already have it made up. It's just trying to help you out here. Quizzes 25%. Again, this would be 100% if it replaced these 2 things. So attendance, it's not part of the grade, but again, can help with understanding. Same with homework. You're going to be assigned a lot of homework. You don't have to do all of it. Everything is going to be off my website. So there's a Canvas, but the Canvas links just to my website because that's where everything is. That's home base basically for everything that you need. The grading is pretty standard grading. Yeah, that's without curving. I don't know if I'm curving. Again, this is all new for me. This is all based on the calendar, so we don't need to really look at this too much. And then I have to include these links in the syllabus. They are important, so if you want to go through them, you can. But I'm not going to waste class time going over them. All right, any questions on, I'm sorry. Yeah, no, I'll just say, is there any questions on the syllabus? This is where everyone just doesn't say anything. This is why live lessons in real life are better. That's okay, though. All right, so let's go back to the website. Or actually, let's go back to this thing here. This is everything that you should already know for the class. Like you should come into the class knowing all of this stuff. Are there any questions on any of this? What I mean by any of it, anything like that? I am setting up office hours for Wednesday. So if you do want to review any of this stuff, all this stuff is also on the website. I'll show you that so you can review on your own. This was also in the email that I sent you, all of these things. Okay. So then we're going to start with a rundown of what today's lesson is all about. So it says Unit 2, differentiation. Differentiation just means finding the derivative. You should know that. There's only 2 parts of this, of the sections that we're going over today that involve differentiation. Actually, let's keep going on the website here. You can kind of see it right here. Unit 2 is differentiation. There's only 2 sections that we're going to cover. If you notice the numbers skip around, that's because Wabanzi does not cover all the standards. They moved vectors for whatever reason to Calc 3. Calc 2 usually covers vectors. That's 2, 3, 3, so that's why it's missing. For the most part, a lot of the other stuff doesn't really jump around too badly. I guess 5.2 does a little bit. But if you go to the website and click on calculus up here, and then click units here, you'll notice that it has a breakdown of all the units here. If you want to review unit 1, which is not covered in this class, but the idea is you have to understand how to use limits for later on in the class. It has all the sections broken down here. It's got videos for every single section here. If you click a certain section, like, oh man, I really forgot how to find asymptotes. I have videos explaining all of that stuff here. I don't know why the practice problems isn't linked on this one, but usually the practice problems are linked here, and then you can go to the practice problems. All of the practice problems have one document for just the practice problems, and then they have another document where it's just the solution guide. I need to match that up more, but the solutions are all listed here. I color code all my answer keys so it's easier to look at and also ask questions on if you do have any other questions. But every single practice problem is going to have that, not just the review stuff, even the new stuff that you're going to be covering for the class. So that's unit 1. Unit 2, there's a lot in unit 2, but a lot of it's covered in Calc 1. So all of this stuff here is covered in Calc 1. This stuff, anything that you see 2 stars on, you notice the 2 asterisks at the end, that's covered in Calc 2. 233 is not covered in this Math 132 class, just 232 and 234. So if you click 232, this is how you would practice. You'd go to it. I make a thing where there's formulas. There's a video explaining how to do certain problems, and then you can click practice problems. Again, there's a practice problems link here. There's supposed to be a link for a video too. I'm supposed to link that, but it doesn't matter. All right, and then the next thing again is the answer key. Again, color coded, complete breakdown of everything you need in order. Let's close this. I also have the book linked too, but the easiest way to get to the book is just to go to this Math 132 here, and then just click online text like I talked about before. We're basically covering the entire book. So some of the stuff, there's okay, maybe a couple things we're not, but all right. So let's go back to here. Okay, there is nothing in unit 3 for Math 132. So if you notice, it goes from unit 2 to unit 4. So that means you really don't have to worry about the stuff in unit 3. You might have to review some stuff, like L'Hopital's rule helps later on, but I can always review that stuff as we need it. Again, vectors are usually covered in Calc 2, but they don't cover it. So you're not going to see 335 unless you take Calc 3 at Wabanzi. That being said, if you take Calc 3 somewhere else, just know they might expect you to understand how to find vector, like derivatives and applying vectors. But you would not have covered that in this class because that's how Wabanzi does it. Other schools do it that way too. It's just, usually it's not. Okay, unit 4 is a lot of this stuff is covered in Calc 1. All of this stuff, all this stuff right here, which is what we're covering this today. 414 and 415 we're covering tomorrow. Again, they don't do vectors, so we can ignore that. And if you are confused on what to ignore, just always go to Math 132. That's home base. I have everything that we are covering, not stuff that we're ignoring. Or I did not include the stuff we're ignoring. We're going over the rest of this stuff here as well. Let's see here. But anyway, anything on this page right here, if it says unit 4, unit 2, whatever it is, you can always just find it by going here, and then all the units are linked here, or you can just click calculus units and it goes here. I number everything like a software designer would, like numbers update. So like 411 here, it's unit 4, section 1, subsection 1. So it's indefinite integrals, and then I break it down into just algebraic. 412 is just transcendental functions. This one's integration by substitution. So it's broken down. That's what the 411 means, 412, 413, and so on. It's just easier to catalog all the sections. And there are 6 units. Unit 6 is completely new. It's stuff we have that's never been covered in Calc 1. So that's why it's got double stars. The whole thing is new for Calc 2. The rest of this stuff is kind of mixed. If you go to like Unit 5, some of that stuff's Calc 1, and then Calc 2's in it a little bit. Are there any questions about the website? Sorry if I'm going too fast. All right. Okay, Unit 2 is all about differentiation. The derivative it just means the slope of a point. So how can you find the slope of a point if You need 2 points to find the slope. That's why you need limits, and the limits allow you to find derivatives. So you're able to find the slope at a point. Again, this is called the derivative. You should know that. Slope of a tangent line, slope of a point, it means derivative. Okay, 232. This is just a preview. We're going to start doing example problems in a little bit. But 232 is all about the differentiation of parametric functions. Now, you should understand parametric functions from pre-calc, but some of you might have not taken pre-calc for years. So I'm going to do a review of what a parametric function is. It's actually not that complicated. It's based on a parameter. In this case, the parameter is t. They always use t for some reason. So what I'm going to do is I'm going to graph this right here. Let me. How can I break this down? I think I have it right here. Okay. So with parametric, your x is defined based on some function with t as the input, and your y is based on some function with t as the input. Usually the x and the y are related to each other, like y equals x squared or y equals x minus 1. The y and the x are together. Here, they're separated, and you use the input as a t. Okay, so it's almost like you have a third variable. But you can still graph the x and the y, and that's what I'm going to show you right here. Let me blow this up. This first thing right here is basically coordinates based on t. So this is an x, this part's the x, and this part's the y. Now, if you put in different values of t, in this case, I'm going from a to b. This is a to b right here. For t, so for example, I can put in a is -5. So if I can put -5 in here, and then I put it in here, and you get some value spitting out, and then it would graph that x and y value. So what does that mean? Let me show you with a graph. So let's do this. Oops. Zoomed in too far. So if you change the a to b and the a and b values for t, it just starts plotting out points. Okay, so you're using the x and the y is defined by some t. In this case, the t is from -5 to 5. And it makes a little graph like this. That's literally the only thing that's the difference between a regular equation and a parametric. You can turn a parametric equation into a regular equation. As you can see, it lines up exactly with it. All you have to do is solve for t and substitute. We don't need to worry about that, though. But that's what a parametric is. And if I wanted to, I can pick different values. So if I wanted to pick 10, it would just keep going. Again, it still lines up if you solve for t, but you don't need to worry about that. Okay, so that's parametric. There's an extra variable, basically. Okay, now this allows you to go thinking, why do we need this? It allows you to do certain things you can't do in a y equals x graph. For example, if I have this cosine, so I'm graphing cosine t for your x and sine t for your y. So x and y, that's basically the unit circle. So if you actually graph this out, it should form, whoops, way zoomed in here. If you graph this out, it actually forms, if you go all the way to 2 pi, it forms the unit circle. The unit circle is actually a parametric function, or I'm sorry, a set of parametric equations that, but they don't really use the word parametric sometimes to explain that. But the only way to make a circle like that, well, not the only way, but the easiest way to do that is with parametric. That's what this is here. And then you can also do something like this, where I made it like weird expressions for the x and the y. And then as you change this, it ends up forming some cool little pattern like that. And again, it's the same thing that you've already been doing. It's just with a t. You don't need to know the basics behind parametric so much as you need to know how to find the derivative using a parametric. And that's basically what this whole section is about. There's a formula for it. This is actually the second derivative. I'm not going to worry so much about the second derivative part. This first derivative, though, is going to be important. And basically, you're just doing the derivative with respect to y over the derivative with respect to, the derivative of y with respect to t divided by the derivative of x with respect to t. And you can see the dt's are basically going to cancel. So you end up with the derivative, which again is just basically the slope of one point, change in y over change in x. That's the slope. The second equation is the second derivative. I'm not going to worry about that. It takes too long to do those problems, in my opinion. And it's just doing the derivative again, so it's not really that big of a deal. That's parametric. We're going to be using these formulas in a little bit. I just kind of wanted to introduce what a parametric is, or reintroduce it, and then talk about how we're going to use it. All right, so 234 is all about derivatives of polar forms. Okay, this was derivative of parametric. With parametric is with a t. There's a parameter t. This one is polar, and you probably forgot what polar is if you haven't had pre-calc in a while. But basically, with polar, in pre-calc or trig or whatever class it was, you had to convert the rectangular coordinates, the x and the y, into circular coordinates, or polar coordinates it's called. So x is equal to r cosine theta, y is equal to r cosine theta. Now this is basically the unit circle. If the radius was 1, x is equal to cosine, y is equal to sine. To find the derivative of this, you just do, it's actually really similar to parametric. You do the derivative of y with respect to theta and then x with respect to theta, and you just divide them. The d thetas cancel. Again, I'm going to show you examples of that. But first, let's review what a polar graph even is. Okay. Ooh, all right, hold on. I don't know why it does this. There we go. Let's do this. Okay, so the way a polar works is it's still on an xy coordinate plane. If you can see, like, this is still y, this is still x, but it bases it off circles. So polar graphs are used for any time you like study something in space, or because there's orbits. Anytime you study something that moves in circles, you're going to want to use polar graphs. It's just easier because, as you can see right here, we have a unit circle. Its radius is 1. So here's the origin. It goes up to 1, and it goes 1 in every direction. You can just say the radius is equal to 1. That's what this says. Let me blow this up. Say the radius is equal to 1. If you wanted to do that with rectangular coordinates, you'd have to write all of this out. And you get the same, let's change the color here. You get the same, let's do blue. You get the same answer here. As you can see, it directly overlaps. But it's a lot easier to write it this way. And if you're going to be doing math with this, it's a lot easier as well, because it's just with radius and theta. And then I just thought this is cool. If you actually take the radius and set it equal to what the theta is, as it goes around, your theta is increasing as you go around. And that's also the radius. So your radius is actually equal to the theta. So it actually forms like a cool little spiral thing. It's called Archimedes spiral, I believe. And I only went to 12 pi. I could have this out for a bunch, but I don't know. I just thought that was cool. I don't really know why I'm showing that, but that's the main thing with polar. Again, you don't need to know the specifics behind it so much as you need to know how to find the derivative at certain points, and we'll go over those examples in a little bit. So that's parametric and polar. We're just going to be doing the derivatives of those. Unit 4 is all about antiderivatives. Integration means well, it means it's involving the antiderivative. It's going backwards with the derivative. But before we go on to Unit 4, let's do some example problems for Unit 2. So take out some paper if you don't already have it, and I would start a new section in your notes, and I would label it, I don't know, parametric differentiation. I guess I should check if there's any questions. Any questions or anything? You're like, what is all these words that he's throwing at me? We're going to be going over a ton of examples right now, so hopefully it makes more sense. Not stop me. You can do this chat thing here or just chime in. Do whatever you need to do. Okay, let's get rid of this. Okay, we have this. All right, so first example we're going to do is, let's say that's, let's say, I'm just making stuff up here. Let's say, I'll just use the same ones as last time. Say x is equal to t squared minus 5, and y is equal to sine t. So let's do that. Okay, right away you should see this is going to be a parametric equation or set of equations because there's a t. So right as you see that, a light bulb should be going off in your head. Oh, this is parametric. That way you know kind of what formulas you're going to need. I am saying that it's on the interval from -1 to pi. So before we even start doing this problem, because the whole point of this is to find the derivative. So we're looking for what is the derivative. The whole point of this is that, but let's actually kind of get an idea of what we're looking at here. So what I'm going to do is graph this out. Actually, Desmos is not the best graph for this. So what I'm going to do is, everyone take out your TI-84 calculator if you have it. I'm going to show you how to graph these on your calculator, because this could come in handy if we're allowed to use calculators on the test. All right, so first thing I want you to do, turn it on. Let's get rid of that. Turn it on, hit mode, and turn on parametric, which is like by the function right here, just arrow over, and then hit enter. Okay, we're going to be going over polar next, but I just want to show you parametric for now. Okay, from here, hit y equals, and get rid of this. And we are going to go with t squared minus 5. If you notice now, this if you hit x, what normally spits out an x, it actually spits out a t. Because if you look right here, it says like x comma t. That t is for parametric. So we have t squared minus 5. And then the other one, I want you to just do t, I'm sorry, sine of t. Okay. Now I want to be on the interval from -1 to pi. Okay. So that means t can only be between -1 and pi. So I'm going to go to window here and then change my t min to be -1, I'm sorry. And then my t max to be pi. And then from here, I want you to do zoom and then zoom fit. So we want zoom 0. And what it does is it fits it nicely to the screen like that. Okay. Now the thing about parametrics is you can't really tell what the graph is going to look like just by looking at these. I'm sure some people can, but it's not intuitive. You can't just go, oh, there's a quadratic and then there's sine. The graph's going to look like this. You have to kind of like graph it to actually see. And what you're doing here is you can see the little cursor down here, but t is equal to -1, but you can just change your t, and your x and your y are based on t. So as t changes, your x and y changes, and then it just graphs it on the xy plane. Okay, so we are looking for what is the derivative of this, because as you can probably imagine, there's ways of drawing tangent lines here. Actually, I'll do this here. Screen grab this. So let's do this here. Ooh. Okay, so I have this graph right here. What I can do is I can draw a tangent line wherever I want. So say I wanted to find the slope, the derivative at this point right here, I can draw a tangent line. So that means there's a derivative there. I can draw a tangent line here. I can draw a tangent line anywhere here. Okay, we are looking for the derivative, which will tell us the slope of all these tangent lines that I drew. That's the whole point of a derivative. It tells us all of these slopes. Okay, to figure out that derivative, we need to use that formula. I'm actually going to go to my website really quick. So you would be doing the same thing if you were doing problems like this and go, oh, I need that formula. So just go to differentiation of parametric, and the formula is right here. So let's see here. We'll shrink this down a little bit. Okay, and you end up with something like that for the formula. Now, we don't need any of this, so I'm getting rid of it. But we do need, we do need this formula right here. Now the formula says find the derivative of y with respect to t. Okay, you should be able to do that in your sleep. So we're doing the derivative of this thing right here. So dy over dt is equal to, does anybody want to chime in and tell me the derivative of that? We're all friends, just yell it out.
Cosine t.
Cosine t, boom. So we have cosine t here. Okay, so we have that part of the formula down. Awesome. Okay, now we need to do this part right here. If you forgot what that means, what this d over dt means, it means take the derivative of whatever's after it. So in this case, there's a y here. I'll just put the y here. This means take the derivative of this with respect to t. So that's what I did. This is already with respect to t, so I did the derivative of that, which is cosine t. This one is take the derivative of x with respect to t. So dx over dt for this one is going to be equal to what?
2t.
2t. Awesome. One person's talking the whole time. I love it. Just kidding. Seriously though, everyone needs to talk at least a little bit. Help me out. All right, so now we have this bottom part now. So we have this top part and this bottom part. To find the derivative, all you have to do is divide those two things. Cosine t all divided by 2t, and then you have your answer. Okay, any questions on that? Okay, it is important to understand that this equation tells you the slope of any of these things right here. Any point you want, it's going to tell you the slope at that point if it actually exists, of course. So given that, let's find the derivative at some points. Let's see here. I'll just use the same points I guess I used for last class. I want you to find the derivative at the following points. So when t, emphasis on t here, is equal to pi over 2, 0, and pi over 4. Okay? So what essentially you're going to do is just plug in these t values to the derivative formula here. Okay? This is kind of a good review for the unit circle because I'm sure some people might have forgotten that. I know I forget it sometimes. All right, so if you plugged in pi over 2 here, to figure out the derivative at this point, you would just have to do cosine of pi over 2 divided by 2 times pi over 2. Okay, does anybody remember what cosine of pi over 2 is?
Isn't it 0?
0, right? And then this cancels here, so you end up with 0 over pi. So the derivative at this one, I did not draw this very well. Hold on. The derivative at t equals pi over 2 is equal to 0. Okay. Now, what this symbol means right here, it just means the derivative, and then you plug in t equals pi over 2. That's all this means. Math's a language. You have to translate it, the derivative, when you plug in pi over 2. So I did the derivative here, plugged in pi over 2, you get 0. Okay. All right, next, whoops. Next, we're going to do the same thing with 0. So if you plugged in 0 here, you get cosine of 0, which is what?
1.
1 over 2 times 0, which is 0. So you get 1 over 0. What is that?
Undefined.
Undefined. 1 over 0 is not 0. You cannot divide by 0. Okay, it doesn't make any sense. How can you divide something up 0 times? You can divide a pizza up 2 times, 3 times, 4 times. You can't divide it up no times. What does that even look like physically? Okay, so that's that one. Undefined. And that does happen sometimes. By the way, check this out. If you actually plugged in, what was it, 0 for t, let's go back to my graph here. So trace, and if I actually went to t equals 0, it doesn't go 0. Hold on, I'll just hit 0 and hit enter. Right there is where t is equal to 0. X is equal to -5, y is equal to 0. What do you notice about the slope of that point right there?
The slope is 0.
No, come on.
What?
Who was your Calc 1 teacher? That slope's not 0. I was this Calc 1 teacher. I'm insulting myself. What's the slope of that? It's a vertical line. What's the slope of a vertical line?
Oh my god, this is so embarrassing.
Someone said it. Someone said it.
Undefined, yeah.
Fine. You're dividing by 0. You have infinite slope. It makes no sense. Because you're not changing with x. If you're not changing with x, you're not changing in an instance, basically. That's why it doesn't make sense. You're infinitely climbing without moving over at all. So that's why it's undefined. And then last but not least, let's do, I guess we'll do blue, the derivative where t is equal to pi over 4. Okay, if you plugged in, what's cosine of pi over 4? Does anybody remember that one?
√2/2.
Awesome. Thank you. Okay, we're dividing this by 2 times pi over 4. Okay, so a cool thing happens here with 2 and this 4 cancel. The divided by 2 and divided by 2 cancel. So you're left with √2 over pi. So I'm going to put something like that. Okay, boom. So that's basically all I'm going to be expecting you to do in regards to parametric equations. I found the derivative, and I found the derivative at points. Found the general derivative. That's what this is right here. This will give me the derivative at any point, and then I actually used it on some of the points. Now check this out. Your calculator actually can find these answers out for derivative at a point. It can't actually find the derivative in general unless you have a special calculator. But check this out. Hit graph, and then do second calc. The second option right here, dy over dx, so 2. And you can write in, what was the first one? Pi over 2? Pi over 2, enter, and you get 0. Okay, it doesn't actually, it's right there. You can't really see it. Here, let's do this. Pi over 2, enter. I still can't see. Oh, you know why? Because it's at the edge. Hold on, let's do this. Let's change my y max to be, I don't know, 2. It's going to change the graph a little bit, and then pi over 2. There it is. Okay, what's funny about these calculators is that literally the technology has not changed since I was a kid, which was many moons ago. So the fact that you still have to spend $150 on these calculators is a joke. That's why I try to use Desmos as much as possible, but that's a whole nother story. But anyway, you see, if you notice right there, the derivative of that is 0 because it's a horizontal line. We did the vertical one already. I can try the pi over 4 one, but it's going to be a crazy, crazy number because of the square root. All right, so 0.450. 0.450. So if you actually do this, you should get 0.450. Blah. Hopefully, yes. Okay, good. Okay. Is there any questions about parametric differentiation? Parametric differentiation, in case someone has questions later on. Whoops, that's right, I already saved one. Let's do this. Cool. Cool. All right, so what we're going to do now is we are going to take a 5-minute break. If you have questions, I'm just going to be sitting here. We can go over whatever you want to go over, and then we'll start polar afterwards. Check if there's, oh no, there's questions. I'm sorry, I did not hear that. Undefined, nope. Oh, people were answering. Oh well, sorry about that. 5-minute timer. Yeah, I'm just going to be sitting here, so ask questions if you got them. Otherwise, get up, stretch, get some water. That's what I need right there. All right, that is time. Is everyone ready to go? All right, I'm just going to assume yes. I have to stop asking questions like that. All right, so here is an example of why polar equations are so helpful. As you can see, you have this satellite going around Earth here, and we have this theta and this radius. The radius is going to change the theta of how many times it's going around, which is obviously going to be closely related to trig. So you're going to see a lot of trig in this, especially here and here. But that's basically the power of polar equations to begin with. I'm not going to really stress that so much because this is a calculus class. The main thing is, can you find the derivative? And can you find the derivative at certain points? Okay. One thing I do want to point out, and I should have talked about this a little bit more in the parametric. If you look right here with the equation, the dt's on these are both going to cancel out. So you end up with dy over dx. It's actually the same thing that's happening over here with the d theta. Okay, the d theta would cancel out. So that's why you can just do the derivative of y with respect to theta and the derivative of x with respect to theta and divide them out, and it still works because those cancel out. Okay, so your function is based on a radius. Granted, this isn't a radius of a circle because this is like an oval here, or an ellipse, I should say. But you get the idea. Okay, let's do an example using this formula, and then we can move on from there. Let's see here. Okay, so the first example we're going to use is, let's do, if r theta is equal to, let's do 2 sine of 3 theta. Okay, I want to know what is the derivative of y with respect to x, just in general, and then I'm going to plug in specific values. Let's just do at theta equals pi over 6. I think that's what I used last time. This is supposed to be an at, like an email. All right. Anytime you see polar differentiation, which is the only time well, I guess we're going to do some integration stuff with it. But if you see polar differentiation, it says the derivative. Right away, I would just take the derivative of r with respect to theta. And this is a good review of chain rule here. Okay. So you have to do the derivative of this right here. And we need this in the formula over here. It'll make more sense as we go. But let's find r prime of theta. So it's going to be 2. That's a constant multiple. And then you have to do the derivative of this sine. And then you wait for the n to multiply by the inner derivative. If you remember chain rule, that's a composite function. We have this function on the inside of it here. So we're going to do the derivative of sine first, which is cosine. The inner layer stays the same as 3 prime. And then you have to multiply by the inner derivative. The derivative of that is going to be 3. So your final derivative for r prime is going to be 6 cosine 3 theta. This should be nothing to you because you've seen this before. Like, this should not be difficult. If it is, then you are definitely going to want to review chain rule because it's not going to go away anytime soon. It's going to be used extensively in further units as well. So definitely review that. It's not just a one-time thing. So we have r prime of theta. Now, the formula states that we need y prime of theta and x prime of theta. Okay, so let's just start with the dy over d theta here. So now we have to do the derivative of y with respect to theta. Well, y is equal to this part right here, r sine theta. So we have to do that derivative, which means we have to use product rule because we have a function r times sine theta. R is a function right here with respect to theta, and then so is the sine theta. So, oh, pardon the noise. All right, so to do product rule, you have to do f prime g. So you have to do the derivative of r times regular g, which in this case it's sine theta, plus g prime, which is cosine theta, times r. Okay, now you can see why we need r and r prime because r prime shows up right here and then r shows up right here. So we're going to need those. Okay, and then we're going to do the same thing with x. We're going to do the derivative. X is r cosine theta right here. So you have to use product rule. So it's f prime, which is r prime, f prime g plus g prime. G prime is negative sign, so I'm going to put a negative there. F, so I'm going to put an R there. Okay, I mean, these are always going to be the same. These are always going to look like this every single time because x and y are always going to look like this. So the derivatives are always going to look like that based on it. All right, the derivative for this would just be this top one divided by the bottom one, but I just want to find the derivative at a specific point. So I'm not going to worry about, I mean, you could just put a divided by sign here, and you get the answer, but we're looking for mostly the derivative at pi over 6. So what I'm going to do is plug in pi over 6 to all of these terms here. So r prime of pi over 6 is equal to, we need the r prime equation with the input being pi over 6. So now you're going to have 6 times cosine of 3 times pi over 6. Okay, so then the 3 and the 6 cancels. You have pi over 2. Cosine of pi over 2 is what? Anybody? We just went over 0. Thanks, Bob. All right, next is so we know that we know this one here, and we know this one here. Now we do sine of pi over 6 because you have to put theta in for that. So let's just start writing this down. So dy over dx is equal to, wait, why am I doing that? It's 0. That's just embarrassing. This is 0 and this is 0, so that's gone. Right, because r prime is 0. So this is 0 and this is 0. It doesn't matter what sine theta and cosine theta are. So all we need to do is worry about r cosine theta divided by negative r sine theta. So r of pi over 6, I should do that one really quick, is going to be equal to 2 times sine of 3 times pi over 6, based on this up here. This is our r equation. This is pi over 6. Jeez. All right. Oops, wrong color. All right. So this is going to cancel to be pi over 2. Sine of pi over 2 is 1. So you should just get 2 for this. So now it's going to be equal to 2. These are both 2. 2 cosine of pi over 6 divided by negative 2 sine of pi over 6. Okay. The 2's are going to cancel. So you're going to be left with negative cosine of pi over 6 is what? Anybody? Nobody remembers.
Root 3 over 2, yep.
There you go,
And
root
then
3 over
half.
2. And then, yeah, 1/2 here. Okay, the divided by 2's cancel. Divided by 2 is 1. So then you get negative root 3 as your slope at that point. Okay, questions on any of this? This is not as fun as parametric because you always are going to have product rule. Product rule takes a little bit. Also, people don't remember the unit circle, so that takes a little bit. Okay, take out your calculator. I'm going to show you how to do this on your calculator to spit out the answer. Again, it will spit out the exact at the point, but it will not actually spit out the derivative itself. On your calculator, hit mode. And instead of parametric, go to polar. Get rid of that. Let's do 2 sine. Was it sine? I think so. 3 theta. If you notice when you press the X button now, theta shows up. That's why it's that third X comma T comma theta. That's why it's there. So we have something like that. We want pi over 6. So as long as that's 0 to 2 pi, that's fine. And I'm going to do zoom 7 because it's zoom trig. It just fits it to the screen nice. And you end up with that cool looking thing. Okay. Now we want pi over 6. So I'm going to do second calc, the derivative. So we want 2 of pi over 6. And if you notice right here, the derivative is as negative 1.732051. If you know the square root of 3, let's see here, square root of 3, forgot to make it negative, but it's equal to that same value. So it kind of shows you that you did it right. On a quiz, if you were allowed to use your calculator, you would have to still, your answer that would be accepted is root 3, not this decimal approximation. But again, that's if we're even allowed to use calculators. I'm still working on that. All right, questions on polar differentiation. Someone's got to have a question. Okay, we just got rock stars here. That's awesome. All right, one way of making this a little bit more complicated, it's not that much more complicated, but it might say like, what is the equation of a tangent line at pi over 6? So what if I was doing the equation of a tangent line at theta equals pi over 6? Okay, so that means we need a y equals mx plus b at pi over 6. Okay, so we know the slope is equal to negative root 3. We just need to figure out the b. To figure out the b, we need the x and the y. To figure out the x and the y, we have an x and a y equation. Just as a rule of thumb, engineers, computer scientists, chemists, physicists, whatever your major is, try to look for the equation that you actually need. Sometimes people go, oh, x and y, I don't know how to find that. Well, look around. There's an x equation and a y equation right there. And if you look around and you can't find that equation, look for something that can lead you to that equation. Okay, what can get me the x and the y? Okay, a lot of times the stuff's right in front of you and people go, I don't know how to do it. And they ask a teacher a question and then the teacher's like, how do they not know where it is? It's right in front of them. A lot of people aren't trained to like actually look for it. So we need the x and the y at pi over 6. Well, we actually found that out over here. Well, not the negative. Okay. So the r, what was the r? 2. Yeah, 2 right here. So the r was 2. So to find the, let's do the y first. It's going to be 2 times sine of pi over 6. Okay, we did that right over here. Except we have the negative in there. So it's going to be 2 times 1/2. So you're going to end up with 1 there. You end up with 1 there is equal to root 3 times x. Well, the x is going to be, it's going to be 2, because x is equal to r cosine theta, cosine of pi over 6. Pi over 6, cosine of pi over 6 is root 3 over 2, so this is just going to be times root 3 plus b. This whole thing's going to become negative 2, or I'm sorry, negative 3, that's embarrassing. B is equal to 4. So now your final equation of a tangent line is going to be this. Like that. For that problem. I don't think I'm going to ask for equations of a tangent line, but just in case I do, you should know how to do that from Calc 1. But I feel like it's extra steps, though. I don't think we're going to have time because the quizzes aren't that long. So maybe I won't. But just in case, there it is. Okay, any questions on this? Well, if you do, I'm giving you 5 minutes right now so you can ask those questions. And then when we're done, we'll come back and do some antiderivative stuff. All right, so that's about time. Let's go over some integration stuff. All right. So this is all about antiderivatives. Antiderivatives are just the opposite of derivatives. They're inverses of each other. It's like you're going backwards, essentially. So integration, when you see integration, just think it's related to something with the antiderivative. The whole reason we have antiderivatives was because they were trying to figure out how do you find the area of any plane. If you know how to figure out the area of a circle, area of a square, rectangle, any basic shape, you're able to find the area of. But what if it's a non-basic shape like this? Okay, is there some formula that actually spits out the area of this, just like we have pi r squared that spits out the area of a circle? And the answer is yes, but you need antiderivatives to figure that out. Okay, 411 is all about the antiderivatives blah, of algebraic functions. Okay, so just very basic algebraic functions. These are the formulas that you're going to need to know. This first one's basically just reverse power rule. You add 1 to the power and divide by that power. You always need a plus c. We're going to go over that in a little bit. Why? You should have actually seen this from Calc 1, though, because even Math 132 covers this. I think this is where Math 132 stops at Wabanzi. Everywhere else, I'm sure they covered it already. All right, you can't do reverse power rule when it's 1 over x. So that's what defines the ln of x function plus c. If there is a constant multiple, you can put it in front of the integral symbol. I'm going to show you that in a little bit. It actually makes things a little bit easier to look at when you do that. Some people don't do it. That's okay. And this last formula, if you're adding or subtracting functions, this integral symbol, this summa, it's called a summa. It's an elongated s. It basically distributes to each of these terms. So the antiderivative of f of x plus or minus the antiderivative of g of x is the same thing as when you do the antiderivative of both of them together, similar to derivatives. 412 is about transcendental functions. Transcendental functions is just a fancy term for it, something that's not algebraic, so it transcends algebra. That's stuff like exponential functions, sine, cosine, inverse trig, that sort of thing. That's basically what transcendental functions are. They have formulas as well, which we'll go over. And the last thing we're covering today is integration by substitution. This is when you have a function that's too complicated to use any of these rules. It's too complicated to use these rules here. So what we end up doing is just creating a new function based on substitution. And this formula right here does not help that much. So I'm just going to show you some examples with that. So hopefully that solidifies your understanding a little bit more. Tomorrow, we're going to go over other integration techniques. This is integration by substitution. There's also a thing called integration by parts, which is pretty awesome. That's the formula for it. And then there's another thing, integration using partial fractions, which has a formula as well. And then that's the entire week. So tomorrow we're only going over 2 things, but they're pretty complicated things. Well, not complicated, but they're a little bit harder than what we're going over today, I would say. So let's start with 411. I'm going to copy this. Actually, I don't think it's going to paste because Google Docs are weird. Never mind, it didn't paste. All right, doesn't matter. All right, so the antiderivatives, the basic antiderivatives we're looking at is like, say you had a problem that was like the antiderivative of 6x. So you're basically, this means what expression has a derivative of 6x? Now, students always get a little tripped up on the symbols. This means the antiderivative of this. This means the antiderivative as well. You need both things to figure out the antiderivative of whatever's in the middle. Okay, I'm going to compare this to the derivative formula. Let's just say the derivative of 6x. Okay, if you notice, you're dividing by dx here. Here, you're multiplying by dx. Okay, here you're dividing by dx. Derivative, antiderivative. Okay, this one, the expression you're taking the derivative of is after the derivative operator. This means take the derivative of this right here. This one, it means take the antiderivative when it's surrounding it. It's really poor notation, in my opinion, because every notation you see, it's usually like sine of x squared, that sort of thing. You have whatever it is, and then like whatever the function that you're using, and then whatever you're doing that function on. So the derivative of this 6x, this sine of x squared. This one, it's like sandwiched in between. It's just poor notation. Don't try not to get confused by that. This is not a thing. There's no dx. You can't do it. Okay, you have to have the dx there. Otherwise, it does not work. So the antiderivative, you're basically looking for what if I took the derivative of something, what would get 6x? Well, the answer for that would be 3x squared. You could probably do that in your head. If you do the derivative of this, you get 6x. But you can also do 3x squared plus 1. You still get 6x because the derivative of this is 0. If you did 3x squared plus 10, still 6x. 100, and so on. If you just keep going, you can change this to any number. You can make it a -3. It's still going to be 6x. So because of that, whenever you do the antiderivative, you would have to write that plus c. Okay, this is a general antiderivative because technically speaking, there are infinitely many antiderivatives for 6x. You don't have to worry about that with derivatives. There is no plus c with derivatives. Okay, you can always test this out by doing the derivative of whatever you have. So do the derivative of this, you get 6x. The derivative of a constant is 0. So you do get 6x, which checks out up here. So that means this is correct for the answer. But you always need the plus c. Do not get a lower grade because you forgot the plus c. Okay. Questions on reverse power rule. I guess I should write the formula down. Jeez. Okay, the formula for this is you just take whatever the function is and you add, it has to be a power function. You add 1 to the power and then you divide by whatever that new power is plus c. Okay, and you can see it worked with our example here. We had 6x to the first. I'm going to add 1 to the power, divide by that, and then do a plus c. So now if you notice, this becomes 2, this becomes 2. 6 over 2 is 3, so you end up with 3x squared plus c, which is what we got right here. Okay, this is reverse power rule. It works if n is not equal to -1. Okay, it only works if x is not equal to -1. Okay, if x is equal to -1 and you tried this, if you notice n is equal to -1 in this case, and you tried using the power rule, it would be -1 plus 1 over -1 plus 1 plus c. But now you're dividing by 0. Okay. Now this is basically saying if you use reverse power rule on this, it's like saying this doesn't have an antiderivative. It's undefined when it's false, that this completely has an antiderivative. If you graphed 1 over x, you could see it has an antiderivative, and it's not that. This actually ends up defining our ln x function. Okay. So the derivative of 1 over x is equal to ln x. Okay. We'll do an example problem a little bit for that, but let's just keep going with our rules. Okay, if you have a constant, let's say we did this, this was our example before, it's actually equal to if you pull the constant out. You still get the same answer. How do I know that? I'll show you. This answer we just did up here, it was 3x squared plus c. Here, let's do 6 times the antiderivative of x is going to be x squared over 2 plus c. Okay, well, if you distribute this out, the 6 over 2 is 3x squared plus 6c. Well, a constant is a constant. It doesn't matter about the 6 there or not. It's still equal to some other constant here. So you don't really need to put the 6 in there. It's redundant. It's already a constant. A constant times a constant is a constant. 6 is a constant. C is a constant and another constant. Same thing. You can pull the 6 out, just like you could do with derivatives. And last but not least, you can distribute. Say I did something where it was like x squared plus 6x. You can distribute that. Usually people don't do this one though. This is often skipped. You can do that if you want, and it's the same answer, just like derivatives. Okay, so that is basic anti-differentiation. That should be a review though. So, are there any questions? Zero. Does that mean 0? I don't know what that means. Okay. Oh, I think I said the derivative of a constant was 0. That's what someone wrote. All right. Thank you for that. Okay. So that's that. The other formulas. Let's do this. All right, here. Just going to grab these really quick here. Okay, you're going to need these formulas to figure out any of the transcendental functions. So say we had something like, we'll use the first one first. Say I had a problem where it was, what is the antiderivative of 3 to the x? Whoops, 3 to the x with respect to x. Okay, this is not something that you can use reverse power rule on. Okay, so do not do this. There's nothing that gets me madder than this. This is really, really wrong. Okay, this only works for power expressions. This is not a power expression because the x is in the exponent. If the x is in the exponent, it's exponential. So you have to use this exponential formula right here. So your a is 3, so you just basically replace a with 3, and you have the answer for this. Okay, the antiderivative of e to the x is e to the x plus c, and then these two bottom ones right here should just be, it's just going backwards. If you did the derivative of sine, you would get cosine. If you did the derivative of negative cosine, you would get sine. So those should kind of be a review as well.
So the exponential one, would it be 3 to the x over the natural log of 3 plus c?
Oh, shoot, that's embarrassing. Yes, thank you. Oh, I appreciate that. Thank you. Good looking out. That's embarrassing. Don't even use my whole formula right. Okay, now if you did do the e to the x one, it would be e to the x over ln e plus c. Hopefully you remember ln e is actually equal to 1 because it's e to the first. Okay, let's rewrite this. So it's e to the first. The ln and the e cancel, so you just end up with a 1 on the bottom. E to the x over 1 is equal to e to the x. So if you ever forget that, it doesn't really matter. If you just use this formula, you should be good to go. I think that's everything for 412. I wanted to give a lot of time for 413 since it's pretty much the hardest section. Oh, real quick, I wanted to show why it's good to pull the constant multiple out. I just remembered. So say you had a problem where it was like 3 over x, the antiderivative of 3 over x with respect to x. What you can do with this is you can pull out the 3. You'll see me do this a lot in my videos because I just like it to look a little bit better. Now you have this 1 over x right here. Now you know that this part right here is just 1 over x, or I'm sorry, ln x. So you can just do that. Some people can just look at this and go, oh, it's 3 ln x. That's fine too, but sometimes it's easier just to pull it out. Yeah. And last but not least, we have the hardest section. Oh, one thing I wanted to show too. I should do this. If you ever have a formula that can simplify it first. So for example, say I had something like this. Okay. You can't use reverse power rule on this because this is technically a rational expression. It's not a power expression. Not the whole thing. It's made up of power expressions, but the whole thing is not. So what you can do is simplify this first. So you can do x divided by x squared minus 1 divided by x squared. So always simplify first is the rule of thumb here. So you have 1 over x and then x to the negative 2 power. So you have 1 over x dx minus x to the negative 2 dx. So then you end up with ln of x minus x to the negative 1 power divided by negative 1. So I'm just going to do that plus c. Okay, so if you start from here, try to simplify. That should always be step 1. Does anything simplify? Can I make anything easier? And if you can, definitely do that. Because some of the practice problems you're going to be doing, you have to do that for. I think that's it for these sections. Any questions before we start 413, which again is the hardest section of today? Covered a lot of stuff here. All right, well, let's just get started then so we have a lot of time for it. So we're doing integration by substitution. I don't know why I wrote that by substitution. Okay. The whole premise of integration by substitution is to get it to look like one of these other formulas that we do have, one of these other integration formulas. So it's going to look like one of these things here, because it's the only thing that you can take the antiderivative of, well, so far as we know for this class. Eventually, you're going to learn some other tricks that you can do for integration. So the easiest way to teach this, in my opinion, is just to do an example. So that's what I'm going to start with. So let's do x times x squared minus 1 cubed dx. I'm going to try to break this down into steps because this is technically a technique. Math techniques have steps usually for the algorithm that you're supposed to do. So that's what I'm going to be doing. First thing I want you to notice is, does anything simplify? And it really doesn't. You can expand out that x squared minus 1 cubed if you want, but that'll take a year. So I would not do that. Nothing else really simplifies. So you have to think, can I use one of the rules that I already know? The answer is no, you can't, because there's no, this looks like it involves power function or power expressions, but they're not isolated. They're all together. It looks like you're multiplying two things out here. So the next step would be to think, can you do U substitution or integration by substitution? And the answer for this one would be yes. Obviously, that's why I'm giving it as an example. Step one for integration by substitution is whatever's the most buried function, meaning it's a function that's inside of another function. In this case, x squared minus 1 is cubed. That is going to be your u. Whatever is the most buried function, 99 times out of 100, that's going to be your u. So step one is to find your u. So I'm going to put a little 1 here. That's step one, is to find your u. You need to substitute for everything that's here. Okay, so this is substituted for. I'm going to put a little check mark here. But we still need to substitute for x and dx. Okay, I'm going to start with the dx. By the way, I did not come up with this. This is like centuries old, this algorithm, but it's really clever. I love it. But the only way to get a dx out of this u right here is to take the derivative of u with respect to x, because now the dx shows up here, which is pretty nice, because now we can solve for it. So now this can be substituted for. That's what we're going to do next. What I'm going to do is multiply both sides by dx. Whoops. Okay, and then you get du is equal to 2x dx. Well, what's interesting about this is we need this part right here, is x dx. So what I can do is just divide by 2. Now you might be going, how do we know we need x dx? It's right here, x dx. So if we divide this by 2, you end up with du over 2 is equal to x dx. That means this part right here is equal to du over 2. So I can actually rewrite this to be equal to, what's in this box right here is equal to du over 2. So I'm going to write du over 2 over here. And then this thing right here is equal to u. So now it's going to be u to the third. Now, if you look at this, you should notice, oh, I can actually do this problem. This is not that difficult of a problem. I'm going to make it look a little bit neater. Again, this is just what I do. You do not have to do this. So you end up with something like this. There is a rule for this. This is a power expression. You can take the antiderivative of that. Okay, so it's going to be 1/2. I'm going to add 1 to that power and then divide by that same power plus c. The thing is, don't stop here. You have to resubstitute your u back in. So this is going to be 8 on the bottom. Just do a 1/8 here. And then so it's going to be, whoops, resubstitute your u back in. So that was the x squared plus 1 right here. So your final answer should end up in terms of x because it started in terms of x plus c. And you have your antiderivative, which is like, holy moly, this is 1,000,000 steps. I also stopped counting the steps. That's embarrassing. Okay, step 1 is find your u. Step 2 is take the derivative of u. Whoops. Jeez. That's step 2. Step 3 is to resubstitute it in. So u, derivative of u, substitute everything back in. Then the last step, well, I guess step 4 is take the antiderivative. The last step is to resubstitute back in. So it's u, derivative of u, substitute, take the antiderivative. This is the worst 4 in the history of time. And then substitute back in, which is the last step. I guess the last step should be check your work. So what we're going to do is we're going to do the derivative of this thing in yellow here, and you should get what you started with, x times x squared minus 1 cubed. So let's do that now for fun. Okay, so you're going to bring the 4 down. We're just doing chain rule here. Minus 1 from the power, divided by 8 still, times the inner derivative, which is 2x, plus 0, because the derivative of this constant is 0. Simplify this thing out. Boom, boom, that's divided by 2. Boom, boom, that cancels. You're left with x, this is gone, x times x squared minus 1 quantity cubed, which is exactly what you started with, so that means this checks out, and you got the right answer. These are rough, okay? But definitely practice these as much as you can because they are not easy. Questions on this? No questions so far. Someone's got to have a question on this. This is very complicated. Or you saw it already, so maybe it's not that complicated. Either way, let me know if you have questions. Does anybody? Technically, we're done now. We just have to go over the practice final, those problems. But does anybody want to see another one of these before we do that? Speak now. Really? Okay. I've seen it in calc before. That's right. Okay, I have a couple more. All right. Okay, yeah, let's do general class questions because I think we need a break anyway. So, Matthew, what did you have for me here? What general class questions did you have? Anybody can speak too if you want. If you have any other questions.
I have a question. Oh,
Yeah, go ahead.
How would homework be assigned? Would we see that on the website or would it just be out of the book?
I don't like using the book personally, and I already made my answer keys and stuff like that, like color coded and a little bit nicer. So what I would do for homework is I would do all the sections. So if you go to Math 132 on the website and you go to the sections, like just open them all up in different like tabs here. And then I would do these practice problems. And then I would go to the next one and do these practice problems. And I would only focus on the practice problems that you don't understand how to do. For example, if you know how to do derivatives already because you are antiderivatives already, then maybe only pick a couple problems and then move on. Don't feel like you have to do all of the problems. I'm not grading them anyway. Okay. So that's what I would do for homework. Nothing's graded. It's all on you. Some people can get by in the class without doing any homework problems at all. Some people need more practice. Everyone's different with math, especially. So that's what I would do. I would reflect and go, what do I need the most help on? What am I most confused on? Now, a good metric to figure out what you're confused on is doing that practice final, because that's the difficulty level that's going to match what your test is. So if you go to the practice final, again, it's on that Math 132 link. Click the practice final. The certain problems we're going to do, we're going to be doing 1, 3, and 12. So can you do 1, 3, and 12? If you can do those problems, no issue, then you know that you're probably good with all those sections and you can, practice not as much as you were before maybe. But it's really kind of a judgment call. I can't tell you practice 8 hours a day because it's going to be overkill for some people. And sometimes 8 hours a day isn't even enough for some people. It's completely like based on the person, I guess. So you have to kind of make that judgment call. Does that answer your question?
Yeah, it does. Thank you.
Okay. I mean, if you want to, again, you can do it office hours by appointment. So if you're like, some people want to like practice with the teacher, I always do office hours after any of these as well. So there's always extra time at the end. So we can go over problems then, like whatever you need. I'm very flexible with what people need. So yeah. All right. And there was another question. So it says, I have a couple more. Okay, about how many hours of class time would you recommend for this course? Again, it's outside study time. It's all based on the person. Some people are going to get it right away. Some people, all they need is a lecture and watching a teacher like follow along with them and they get it. Some people need to practice, 5 hours a day. Not 5, that's ridiculous. Ideally, maybe, I don't know, a half hour a day is like what I'm shooting for. I don't give too many practice problems. I always give enough problems, like, so you'll have plenty. You'll have more than you'll ever need. But my practice problems are very concise to focus on, your thinking. The one thing you don't want to do in this class is become a robot. Okay, because what sometimes people do is they become a robot. Oh, I know how to solve this problem. They go into robotronic mode and they forget something little, or they forget some little trick or something else they want to do. You want to almost like for sports, you want muscle memory, because that way you can react the way you need to react at a certain time. With math, you really don't want that. If you have like muscle memory for math and you're just constantly going through the motions, you're going to forget what you're doing and why. So a good hint that I would, or tip that I would do for like conciseness of things, is look through this. You should be able to explain why for every step. Okay, so from going from here to here, why did I do that? Why did I do the U? How many people can answer that right now? Why did I do the U? You should know that. Okay, why did I do this step then? You should be able to I feel like math should be taught where like every step should have a why, and you have to answer that. But some people don't do that. They just go through the motions. I've had people in calculus that don't even know what a derivative is, but they can calculate a derivative. They can use all the rules and do everything, no problem, but they don't even know what they're doing. Okay, like that's what I don't want people to do, is you should always know what you're doing and why. So try to focus on the quality rather than the quantity of study time. If you can't answer why for each step, then you need to ask a teacher. That's why I get paid. Like, why did you do this step and this step? Or why do I need to do this step? Like, you should understand every little piece of the algorithm. Algorithm is just a process of solving something, of doing something. So you should know why you did that. Okay, I don't know if that really answers your question, Matthew Seidels. So it sounds reasonable. Make sure you keep up creativity when solving these problems and make sure you know the why. Are there any outside? Yeah, I mean, I would use my videos. My videos are a little bit different than some other people's because I actually have conceptual videos as well as example problem videos. So I try to so you understand the basics behind it, because in AP Calc, there's a lot of tricky questions where they give you questions where you've never seen them before. Like a students yell at me and go, "You never went over this problem." Like, we did, but AP or any professor will make problems that are completely ridiculous and like curveballs where you really have to know your stuff inside and out. Some people just know the problems one way, but to know them fully around, the front ways, back ways, every single which way, that's the main thing that you need to focus on. I don't focus on that in this class because, one, it's a summer class, and two, we just don't have the time. If we were meeting every day or something like that, I would give those rigorous problems, but your problems are mostly going to look like this problem, these problems here. I'm not going to catfish you with a test. I always hated when professors did that. Your tests, the problems look like one thing, and then the next thing you know, the problems look all different. Like, that's really unfair and stupid, especially since every other test you take, you know what's on it. You know what's going to be covered on it. It might look different, but you know that, the SAT is going to have a reading section and what the reading section involves. So I try to be like that as much as possible for this class. I will try not to give curveballs. A lot of this stuff is very procedural. So it's just the nature of the class, I guess. So, okay, for Monday quizzes, is that the only thing that we are doing that day, or are we also doing a class period? I was only going to do assessment that day. So what essentially it's going to be is you actually have to turn your cameras on. So everyone's going to have their cameras on just like how they are now, only everything's off. And then I have to be able to see your hands, like just so you're not using your phone and stuff like that, because a lot of this stuff you can solve with photo math. So they're making us proctor you. So and eventually the college is going to proctor you. But they don't have that set up yet. But eventually, you're not even going to meet with me. I give them a test and then they give it to you. I don't like that though, because I like answering questions during tests. Like when someone goes, "What did you mean by this problem?" I want to be able to answer that. If you forget a formula, I can tell you. A proctor might not be able to tell you because if they don't know the formula or whatnot. But so eventually you're going to be when we do a Monday's quiz, you're going to be in the video and I'm just watching you. I'm just sitting there. I'll be on mute and you're just taking your quiz. That's why one of the questions was for that survey, do you have reliable access to the internet? Because if you don't, you can't really be in the class, then you'll be dropped because you won't be able to take any quizzes or tests. I do ideally want it to be just quizzes though. I think I went over that. Are those, if you want it to be at 1 p.m., you can, yes. Actually, I'm going to probably change the times because 2 people signed up for my 5 p.m. class. That'll be the 3rd time I've taught this. So it's 6 hours a day of me teaching the same lesson. So I think I'm going to just make it where there's 2 meeting times a day, because 6 hours is a lot. They don't pay me for that much. They only pay me for, I think it was 3 hours every class period. So that's 6 hours a week. I'm going to be doing 12 plus the quiz. So I'm not saying that because it's pay and stuff like that, but you know, this is just one class and it's taking up more time than if I was teaching 4. So it probably won't be 1. To answer your question, I'm probably thinking about 2. So maybe 1 at like 10 a.m. and then 1 at 2 just to spread it out. And if people can't do it that day, then I'll be flexible, but that'll be like on an individual basis. I'm very flexible with stuff. So, but to have a 2-hour lecture for 2 people is kind of ridiculous in my opinion. I'm not trying to be lazy though, I promise. All right. So for Monday quizzes, the only thing we're doing, oh yeah, so I answered that question. And then we have class on Tuesday and Wednesday. Yes, Stephen, that is correct. Starting next week, Tuesday and Wednesday will be lesson days. If there is time at the end and I'm not doing anything else, I will gladly meet if you want to, talk after the quiz, doing office hours, whatever. That's totally fine. All right, that sounds reasonable. I think I read that one already. Yep, the why. Are there Monday quizzes at 1? Yeah, I answered that. And I'm sorry for flip-flopping on stuff. And it's just, I've never done this and I want to, it's better to be over-prepared and then whittle it down from there. So that's why I'm cutting one of the times. So any other questions? All right, so I'm going to spend the rest of the time going over that practice, the practice problems from the final exam. If you do not want to see that, be here for that. That's fine. You can always just come back and watch the video later or whatever. I don't have the answer key up. I guess I should post that. And I will do that. So is that cool? So if you want to stay. We're going to go over the practice test. Otherwise, I will see you later. I'm not offended when people leave either. So I do not judge. We all got lives. All right, so let's go over this practice final. Zoom in here. Screen grab really quick. All right. So this one says find the slope of a tangent line. Whoops. Of a slope of the tangent line to the curve, that curve at that theta value. All right, so let me see if anyone's even still here. All right, cool. Laith, I'm sure you're going to want to get in on this. Do people want to talk through this? It doesn't have to be me just lecturing. Let's talk it through together. You cool with that? I only know Laith and Steven, so if you want to chime in, though, by all means, unmute and we can talk this through together. It's better to do it that way. It's one thing to watch me do it. All right, what do you got, Laith? What should we do?
Let's first take the derivative of cosine 2 theta.
All right, so let's do that. What is the derivative of this? Anybody?
Is it -2 sine 2 theta?
Right. -2 sine 2 theta. You need a chain rule for this. So I did the derivative of the outside layer, which is that negative sign, and then you multiply by the inner derivative, which is that 2, to get all that. Anybody have any questions on that? All right. So to find dy over dx, we need to take the derivative of y divided by the derivative of x when it's in terms of theta. Let's do this here. All right, so if you remember, this is the nightmare that we had to go over before. Dy over d theta.
Oh god, there's a problem with your mic a little bit.
Oh wait, what happened?
There's a buzzing sound. There's a buzzing sound in your mic.
Sure, it's me. Is anyone else getting that?
I can hear it too.
Yeah.
Is it still there?
Yeah.
Is it any better?
Yep, much better now.
Uh-oh. Hello? Check 1, 2. All good now.
Okay. You're good, you're good.
Is it better, Laith?
Yep. Much better.
Hello? Uh-oh.
Hello? Can you not hear us?
I'm talking, but no one can hear me, apparently. Oops. I can't hear you. There we go.
Hello,
check.
Hello? Check.
There we go. Yeah, okay. I have a microphone. When I unplugged it, and plugged it back in and turned it into the speaker. Okay, sorry about that. Now I can hear you.
All good.
All right, cool. So one thing you have to remember is that y is equal to r, whoops, not cosine, that's embarrassing, sine theta. X is equal to r cosine theta. Okay, so now we have to do the derivative of both of these, which is, I didn't really leave enough room here. So y prime with respect to theta is r prime sine theta plus r cosine theta. And then this one right here, same thing, only everything's flip-flopped. Whoops. Minus r sine theta. Okay, now we're dividing these two things, but we have to plug in pi over 4. Okay, so it might be a good idea to find what r prime of pi over 4 is. Here's your r prime equation. Remember, whenever you're looking for something, look for the general equation and then plug it in from there. So you're going to end up with -2 sine of pi over 2 because you're multiplying pi over 4 by 2 here. What is sine of pi over 2?
1. So it's -2.
-2, good. All right, cool. Now let's also find the r of pi over 4 because of this part right here. So what is cosine of pi over 2?
Just 0.
0, which is awesome because that means this is gone and this is gone. I'll try to do that every time so you don't end up with having to add stuff. Just make it easier for you. All right, here we go. So now we know that dy over dx, oops, at theta equals pi over 4 is equal to this divided by this, but you still have to plug in the pi over 4 for each of those. We already know about r theta. Whoops, that was not supposed to happen. All right, sine of pi over 4. Oops. Okay, is there any questions so far? Okay, the only thing left to do is solve this. This is equal to 1. Tan of pi over 4, which is sine over cosine, is equal to 1. So this ends up just being 1.
Yeah.
So for the polar differentiation, that's what we just did, right?
Yes, correct. Yep.
So when you do that, the coordinates for x and y are always going to be the same?
No. In this case, here, let's kind of skip. I didn't skip some steps.
Maybe I'm not asking my question correctly. So like where you have an orange, the y, yep, the y equals.
Oh yeah.
That's always going to be the same?
This is always true. Yes, that's by definition correct. Like you had to go over it in pre-calc. I'm actually like, oh, actually no, I just figured out. Here, this is so like overkill. But in case anyone cares, oops, I didn't want to do that. So the unit circle is 1 for the radius around. That's why it's called the unit circle. And this is the worst circle in the history of time. All right, sorry, it's hard to write with this thing. So the radius is this thing right here. If you change the x and the y for all of these, you should know that it's always going to be cosine and sine. That's just a review. The r is usually 1, but say you were making the circle bigger, like out here, say the r was 2. Now the x value is just going to be whatever it was here times 2. So that's why it's 2 cosine theta for the x. Whoops. You don't really need to know that, though. That's so sloppy. This is being recorded. Jeez. All right. But yes, this is always going to be true. You have to know this. Oops. That's part of the reason why it's on the, if you go to my website, that's why it's on that section. Like this is like the stuff you're supposed to know, and this is the new stuff, the derivative part.
Okay, that makes a lot of sense. Thank you.
No problem. Okay. So sine of pi over 4 is actually equal to root 2 over 2, and then this is also equal to root 2 over 2. That's why it was equal to 1. You could do tangent of pi over 4, and I just knew that that was 1. That's why I did a shortcut. I shouldn't do that, though. It's my fault. Let's see here. So that's why that's 1. So that's the answer for this one here. Now, if you check with your calculator, where's my calculator? So if you check with your calculator here, let's do, what is it? Cosine 2 theta here, graph it. And if you do second calc, the derivative at pi over 6, or was pi over 4? That's, yeah, pi over 4, and you hit enter, it tells you that it's 1 as well. It's kind of a shortcut way of doing it. But just know you do have to show work on this. So even if you use your calculator to test the answer, you still have to show all the work for it. Is everyone go with number 1? Okay, let's do number 3 then. All right, who wants to take lead on this one? This one says find an equation of the tangent line. So you need the y equals mx plus b for it.
Should I take it again?
What's that?
Should I take it again?
Oh, I don't care. Yeah, if no one else is going to do it.
All right. I guess we're going to take the derivative of x and y with respect to t.
Yeah, let's do y first, just because it always was on the
Y.
top.
All right.
Yeah, it doesn't really matter what you do, though. Okay, so everybody do this now. This is always step 1, because the formula, if you remember, it's dy over dt over dx over dt. These are always so easy, too. Like, the functions are always super easy. Okay, you should get something like that. Okay, it is important to note that we are looking for when t is equal to 1. Okay, what's the next step?
2t plus 1 over 2t minus 1.
So I'm just filling in here and here. Okay, and then last step.
Just plug in 1, right? Yep.
Plug in 1, boom. So what are you going to get, 3 over 1? Okay, and I also want everyone to check it on their calculator just to make sure it's right. Okay. This is also good practice to make sure you know how to go back to parametric. If you ever forget a calculator thing during a quiz or something, just ask me. Usually pretty lenient with that kind of thing. Where am I at here? T squared minus t. Cool. Three, boom. Oh, wait, I'm not even done yet. This is, man, I'm making a bunch of.
Find the slope intercept form, right?
Right. Yep. Equation of a tangent line. Okay. So we know that that's the derivative, but that's not the answer that we're looking for. So you have y is equal to 3x plus b. Okay. To find the b, you need the x and the y. Do we have an x and a y equation anywhere?
Yes, it's given in the problem.
It's given in the problem. Okay. So if you plug 1 in for y, for the y equation for t, plug in 1 for t into the y equation, you end up with 3. The other one, you end up with 0.
Just be 3. Yep.
So your final answer, y equals 3x plus 3.
Yep.
Now, you can't actually do this on your calculator because for some reason it doesn't spit it out, but you can look at your calculator and see if this is reasonable. So if you go back to your calculator, actually you can see that it does intersect at 0. Right there, you can see, boop. Now, one way, I mean, this is kind of a cheater code thing here. You can just change x to t, and then you can just graph 3x plus 3. Because x is t, it's basically 3x plus 3. And if you notice, it does intercept there. It does graze that area, that spot. You don't have to do that, but I mean, the rest of it's algebra. If you should be able to figure out the b. Okay, questions on this? Okay. Ready for the hardest one here. Number 12. U sub. Hey, holy moly. What should our U be?
ln x?
Okay, ln x.
Since it's going to be, when you take a derivative of 1 over x, so that's going to, so we have a 1 over x.
Yep.
Yeah.
So our u is definitely this ln x because the derivative of ln x actually shows up in the problem because this is technically 1 over x right here, which we're going to need to substitute for. So du is equal to 1 over x dx. So that means you can rewrite this whole thing to be what?
Cosine u du?
Cosine u du. Okay, because this 1 over x dx, this part right here, is du. It's just abstracted away into that du. This u right here is ln x, so it's cosine of u. If you notice, you now have a formula that's very, very easy compared to where we were at before. You should have a very easy antiderivative. What is the antiderivative? Anybody?
Sine u plus c.
Sine u plus c. Boom. I love it. Okay, and then you substitute your u in. If you want to just substitute your u in right away, you can do that. I don't know why I wait. Boom. Now what I would do is I would check the derivative of this to see if it matches. It's always a good idea to do that. So if you do the derivative of this, you would end up with cosine of ln x times the derivative of ln x, which is 1 over x, plus 0, which is where you started. So we are good to go with this. I usually put a little check mark there. That means I checked it. And that is those 3 problems for the final. So if you can already do these, you know 1/5 of the final already.
I'm excited to go over the serious questions.
Oh yeah,
it's gonna get there.
It's gonna be insane.
Yeah.
Talk about like it's so pointless, like especially in terms of engineering, but they make you learn it. But it is still good math. It's good thinking.
Yeah.
But I think you'll like tomorrow's lesson too. It's just with integration by parts and talking about problem solving and using the algorithm and stuff like that.
Yeah, I'm definitely gonna like by parts.
Yeah. You're. So, all right. Any other questions from anybody? Well, all right then. That's all I got. If you do have any questions, you can email me or text me. Or actually, I don't know if I went over how you could text me, but it doesn't matter. Just email me, and then tomorrow we'll meet the same time. And yeah, that's it. All right. Take it easy.
All right. Thank you. Bye.
No problem.